We define the magnetic flux phi through a surface in direct analogy with the electric field flux used with Gauss's law. We can divide any surface into elements of area dA. So here's a little area element dA as shown. For each element we determine the components of the magnetic field vector B, normal and tangent to the surface at the position of that element as shown. In general, these components will vary from point to point on the surface. From the figure, the perpendicular component, we can see that this perpendicular component is B cosine phi, the angle between them, okay? So B perpendicular is B cosine phi, so I've got that written here. We define the magnetic flux phi, this, through the area as perpendicular component of the magnetic field dA as B cosine theta dA, and that's obviously, we know that that part there is the dot product. So the total magnetic flux through the surface is the sum of the contributions from the individual area elements given by this. So we're going to look at we're always going to look at these perpendicular components, and we're going to sum them all over the area. So that's what we're doing with this. And as we've said before, B cosine theta just becomes the dot product of B delta A. In the special case where B is uniform over a plane surface with total area A, then we've got the situation here, we can bring out, because that's going to be a constant now, because it's uniform, we can bring it outside, and we're just left with, that reduces nicely to BA cosine theta. And now if B happens to be perpendicular to the surface, then obviously if it's perpendicular to the surface, then theta equals 0, and we know that cosine 0 equals 1, so that nicely reduces down to theta equals BA. The chief utility of the concept of magnetic flux is our study of electromagnetic induction, which comes later. The definition of magnetic flux given previously has an ambiguity of sign associated with the direction of the vector area element dA. In Gauss's law, we always took dA as pointing out of a closed surface. Some applications of magnetic flux involve an open surface with an edge. So, you know, it's not like just a sphere anymore, it could be just some arbitrary surface which is not closed. In these cases, we define the direction of dA as follows. If we always walk with an anti-clockwise direction in the area, then from your feet to your head, that will be the direction of that vector dA, yeah? So whenever you see the vector dA, you can work out its direction using that convention. If the element of area dA, this element here, dA, is at right angles, in other words, the theta is 0 to the field lines, B perpendicular is B. So we're seeing here B perpendicular, if the angle here is 0, then cos 0 is 1, so B perpendicular is B. In this case, B then equals the flux divided by the area. That is, the magnetic field equals the flux across an area at right angles to the magnetic field. So we can see it's right angles to the magnetic field. B is sometimes called flux density. Since the unit of flux is 1 Weber, the unit of field, 1 Tesla, is equal to 1 Weber per square meter. We can picture the total flux through a surface as proportional to the number of field lines crossing the surface, and the field, the flux density, as the number of lines per unit area.